Hi guys, in today's video we'll discuss fundamental principles of Newton's second law with both an observed and theoretical model. This video will test an object to see if it has constant velocity and a straight line, reflecting zero acceleration of an object, which indicates that there is zero net force on the object. In layman's term, it means an object will not accelerate unless there is some force applied to it. We could thus say if an object decelerates or accelerates, there must be some kind of net force acting upon it. We say that the formula applies where we have a final momentum is equal to the past momentum plus some kind of force over time, and thus by dividing out the mass, we could get a final velocity equals initial velocity plus some kind of acceleration over time. And given if our acceleration is zero, then our final and initial velocities would be the same. Thus, if a force did exist, the final initial velocities would be different. It would imply that there is some kind of acceleration, which would also imply some kind of net force exists. So to set this up, we will have a battery set down a ramp, and upon hitting the flat table, it will no longer be accelerating. Hypothetically, if there was no net force, there would be constant velocity. If there was a net force, there would be a change in velocity. We are going to measure acceleration and velocity upon its arrival on the table to verify if our hypothesis is true. Then, using a theoretical model and an observed model, we could compare the motion changes and say whether there is a zero net force enacting on the body of mass, aka the battery. I then set a monotonous white background to properly calibrate the auto tracker for observed model. This helps eliminate human error. The distance traveled is calibrated with a roller next to a rolling battery. The x-axis is set to the point of origin, see the center of the battery, upon its arrival on the table, and is auto-tracked for 0.767 seconds. The x-axis is calibrated to follow the object's center of mass, where the positive direction is to the right and the negative direction is to the left. There are still some errors with the software, as there are some discrepancies in the calibration techniques. This discrepancy is noted in the y-axis, as there's a plus or minus error in the thousands of meters, indicating our path of travel is not entirely straight, but this is negligible due to the y direction being in the 1/1000th error, which is close to being straight. More discrepancies are left near the end of the video. The main points still stand. There is an object of some velocity, changing or not changing, in the x direction, and is automatically tracked to a fairly accurate degree. Now let's discuss the hypothetical model. First, we'd assume the following conditions are true, given they are the same initial conditions as our observed experiment. If there is no net force, implying no acceleration, then the theoretical model is true. This model assumes constant velocity, and we can use this assumed constant velocity to compare against our observed model to see if they line up or not, as this will indicate if we have varying velocities, indicating that there's a net force. Both models are extremely close, as seen in the spreadsheet provided. The theoretical model is slightly off, but when adjusted for sig figs, will display values even closer to the observed model. As seen, the relationship is linear between displacement and time, with an r value of 1 to verify they are a linear relationship. This linear relationship between displacement and time implies constant velocity. With all this out the way, let's discuss about discrepancies and questions. Here I've taken the theoretical model to its limits to even more significant digits. This will get us as close as possible to the observed model, and you can see just how much we are off by. To see how accurate the model is, I've also showcased a long list of data points collected. Assuming the final, initial, and average velocities are the same, we could compare the theoretical and final velocities of our observed final velocities. We could observe that they are the same, as we have previously established they both travel with no accelerating nor net force. So as we can see, the difference is not by much. The left column is time, with the right column being displacement. We can see the difference between observed and theoretical is negligible in this extreme. So what causes this extreme small variation? Well, the auto tracker was calibrated with a rough ruler measurement background instead of precise ways of measuring a change in position, i.e. an infrared laser to verify distances were crossed by the object at that said time. Plus, if the building or table is at an incline, the force of gravity would be a consideration. Software limitations, such as being off by a few pixels or incorrect y-axis, could have also played a role. These errors are negligible, but they should still be noted for such small discrepancies. Regardless of error, the numbers are still going to have a r value of 1, indicating a linear relationship. And so this ties back to a viewer-asked question of how many forces are applied to the body to give zero net force. And the answer is it's hard to say, if not almost impossible. As we've discussed earlier, minor software limitations and lab setup masks most attempts at defining the forces on the body. Additionally, there are more forces than just friction in this world. With such a small room of error and much overlap with software errors, it's nearly impossible to say how many forces are applied to the body, if any at all. Another viewer asks, what happens if we flip the x-axis? My x-axis is now positive instead of negative. This would graphically look like a mirrored image of our previous observed versus theoretical model. It's mainly the sign that changes in this case, and if both the positive and negative directions are taking their absolute values, they'd be numerically the same. Overall, it wouldn't change anything in terms of finding the net force and acceleration, although the positive would indicate the object is moving in the opposite direction of our previous negative, aka it's now to the right. So, in summary, there's two potential observations that you can make from this lab. One is that there's no net force because the object does not decelerate, at least by any applicable quantity. Arguably it's computational error that contributes to not seeing it. This is most likely the observation that most of my colleagues will use. However, there's a second, less used but still viable option, and it's that there is still a net force. It's just really small but still applicable to our object nonetheless. Anyways, I have a representation and short clip of trying to get this single answer between the two.
It's just not fair, damn it!
Oh no, it's the end of the little slideshow. Well, I'll see y'all next time. Goodbye and have a safe day.